Cool. So let's get started, guys. I'm Dhruv. Like a brief introduction about myself. So I'm Dhruv. I right now work at Pype. Before starting Pype, I was at Facebook. I spent nearly like half a decade there. At Facebook, I built products like Facebook Marketplace and Instagram Shop. There, my main focus was more on the backend side and especially on the machine learning services. So yeah, that's a little bit of introduction about myself. Today, I wanted to kind of just talk about this new model DeepSeek, mostly from the architectural point of view. I know that there is a whole geopolitics going on about like if whatever they are claiming is right or not and stuff, but who knows? The architecture of it and the kind of things they have done is pretty interesting and very exciting. So both me and like all of my colleagues in Pipe, which include Surya, Deepesh, and Ashish, which are here in the meeting, we have been like talking about this and we have been reading upon this. So I thought I'll just kind of put together a few thoughts and share that with a larger audience, and also like kind of gives me an opportunity to learn from other people. So this session is not like a session which I'm taking. It is actually, but more like a discussion. So if you guys find something interesting or want to kind of ask me anything, please feel free to interrupt, raise a hand, or just like unmute yourself and say it out loud. Cool. Just to check that if everyone, I see that we have few more people now. Cool. So I'll get started. You know the rules. If you find something interesting, you can just say hi or just like kind of raise your hand in Zoom. So yeah, let's get started. In next, I would say nearly 35 minutes, we will cover these particular topics. We'll start with like how LLMs have evolved in terms of their architecture. This will help us understand the architecture of DeepSeek much better. And then we will compare like current state of the art models like O1 and DeepSeek, or Deepseek R1 to be specific. And then we will talk about like if you want to use DeepSeek, how you can use it and what are the use cases where DeepSeek works best, where it doesn't. So let's talk about the architecture first. So if you see like, and this is not like a very long history, I would probably say let's start from like 2010, 12-ish, when like RNNs, that is recurring neural network, they used to be like market leaders, or they used to be like talk of the town in computer vision and image recognition and like many other fields. Soon after that, nearly around 2017, transformers, like you might have heard of paper attention is all we need, that transformer paper came out. That was initially designed for language translation. So like if you have something in English, translate that into French or some other language. That was the like at that point of time, those were the things which machine learning was doing. Like text generation and all these things were not even imaginable. So transformers came out mostly from this point of view that okay, we can translate English. Soon after that, people realized that there are multiple other things which you can do with it. They understood a very interesting concept of attention, which we'll talk about briefly in next few minutes. But then after that, like these language models started evolving much faster. So then came out bidirectional autoregressive models. Then companies started putting in more and more money and data into scaling and sparse architecture. And then came out reasoning and specialized architectures, putting things in more like these are lot many jazz words, but putting things more in perspective. So starting with like RNN, the first thing which came out were transformers. Then came out like GPT-1 and 2 of the world and BERT by Google. Then came out GPT-3 somewhere around, I would say 2020. And then now at where we are right now, so 2024 and 5, we are seeing newer models like GPT-4, O1, DeepSeek V3 and R1. These are the like state of the art model right now, which we call as reasoning models. Let's go a little bit deeper into each of these stages. Like if you remember these stages, let's go a little bit deeper into that, how the architecture has evolved, what kind of research has been done to make these models much more efficient, much more intelligent to the situation where we are today. So when we started with transformers, they were initially more like that everything was like there was a concept of self-attention. So it's like if you take this example of the cat sat on a mat, this is like one example which we'll follow through the rest of the slides too. Everyone would pay attention to every other word. So like if you pick any word like let's say cat, It'll pay attention to it'll pay attention to sat, on, the, mat, and there will be multiple other combinations too. So like this is called self-attention. Similarly, sat will also pay attention to every other word. So you see, there is no direction to it. It's just that like one word is, by paying attention, I mean like if you consider one word called cat, you would calculate probability that how often will cat come in front of sat, and how often will cat come after the. So these kind of probabilities is what attention is, roughly put. I'll cover that in more detail later, but just to make a mental picture that how probable it is that cat and sat will come together, how probable it is that cat will come on second place and on will come on third place. And similarly for the and the mat, same thing for like all the words. So you see, like there are so many permutation and combinations involved. This is called self-attention. It's highly inefficient, but back in the day, this was the state of the art. And this was very useful in language translation, mostly because the sentences which we form in English or Hindi, like the structure could be different in French or Spanish. So you don't have like a direction to it. So this was called self-attention. This was described in the first paper of Transformers, attention is all we need. Soon after that, people realized that it's not probably the most efficient thing, but if we kind of find out certain use cases, then we can actually make it much more efficient, much more intelligent. So then they kind of filtered out few use cases. They say, okay, let me start fill in the blank kind of a use case. Let me start talking about that. So then researchers said that if we consider these kind of problems, then these kind of problems are very important when you are talking about like data correction, data generation in general. Like in if someone is data scientist in this group, they will understand missing value treatment. So these kind of models or these kind of techniques or technology was very important to them. So then BERT came out. They were like, if there is something missing in a sentence, I can actually tell you what that is by using the same attention, but not in a self-direction way, because that's like too compute heavy. It takes like a lot of data to train that. Let me do a bi-directional one, that I'll pick one word and find out what comes after this, sorry, what comes before this, and what all words can come after this. So similar probability, but instead of self-attention, it became bi-directional attention. Are you guys following me so far? So in a similar example, the dash sat on a mat, it will be easier to predict that it was a cat which sat on a mat. So it's a very specific use case based model, which is used for missing value treatment, classifications. Like if you have just one word answer to a certain thing, classifying something into one of those categories, BERT is pretty good. It does bidirectional treatment of that missing value, and it will tell you the answer. Much more efficient than self-attention. Cool. So moving on. Soon after the bidirectional architecture came GPTs. This was when like things starting to get a little heat up. They were like bidirectional is also pretty, like this was mostly OpenAI. They said that bidirectional is also pretty inefficient, and classification is okay, one of the use cases, but there are other ways to do it. There are other kind of classification model which are much better at it. Now let's try out language models for other things, something like generation, like text generation. So then they were like, and text generation happens one after another. So you don't have to go backwards, or you don't have to relate everything with everything. All you need to do is just identify what was the last word and what will come after that. Similarly, if you keep on predicting the next word every time, you will have the answer. So then they came up with unidirectional attention. So these were called autoregressive models, which was the first GPT 1 and 2. To put things simply, in this case, it will be like, if I am saying it's a fluffy blue, then what is the probability that it will be a creature, right? Let me take another more detailed example to explain this, but understand the direction, how direction is changing from self-attention, where it was no direction, to bidirectional, where things became like center and outwards. And now it is just unidirectional. So you see how the models are getting much and more efficient and becoming more and more specific for their use cases. Just talking a little bit more in detail about that. So what will happen is, like, let's say if you tell a particular model, I'm explaining autoregressive model, and if I'm talking to it and saying that a fluffy blue creature, so it will pay attention to creature. It will say that it, like if you let's say if you're talking about just self-attention, then it would generate something like this: a fluffy, this could be fluffy; blue, this is something blue; a creature, this is something which is a creature. But in reality, you are not saying that. You're not describing that in how you speak in your language. So GPTs would understand this. They would see that creature is what you are asking for, and you have written a fluffy blue creature. So it will ask like what came before it and what came before that. So then it can combine that. This could roughly be called a context. So now creature will have two contexts right before that. So it can create a fluffy blue creature for you. Similarly, like a different example, but on the same lines, that verdant and forest. So now forest could be a verdant forest. So it will be like more like a greenish, lush green forest. So you understand like how the context is being carried in a much more efficient way. A creature would understand that what adjectives came before it, and it will generate that creature accordingly. So now it became much more easier for you because you have unidirectional context carrying capacity, that you can predict the next word. In this case, it could be an image or it could be something else, because nowadays these transformers are being used across multiple models, not just LLMs, but also across image generation, music generation, and whatnot. So whatever you are trying to generate would carry the context from words before it. That was the whole point. And it's all unidirectional. Creature would not know what comes after it, like if a verdant forest will come after it or not. It has no idea about it. It does not care. If you just write a fluffy blue creature, it will generate a fluffy blue creature. This was the whole notion of unidirectional attention. Talking a little bit more about attention, that why it is called attention. So if you see that there is a creature which is the target for now, right? And there were two adjectives before this, blue and fluffy. They attend to creature, like they basically somehow influence it. They pay attention to it, or you could also say that creature, like this particular word, pay attention to what came before it, right? So that's why it's called like attention. And many a times it has become a much famous quote now, that attention is all you need. So that was the like this is the underlying thesis beyond, like beneath that, actually, right? So if we have any questions, I know like we are kind of skimming past through these very dense concepts very quickly, but since we are a little short on time, so I'll skim through them. But if you want to understand anything, please feel free to interject, and I would be more than happy to answer. Cool. Moving forward, we have achieved autoregressive models. We had like GPT-1 and 2. GPT-2 was what, 1.5 billion parameters. It was okayish. It was not like, I would not call it best model, but it was okayish. It proved certain hypotheses wrong, sorry, and certain hypotheses right. Then people at OpenAI and some other researcher realized that what if we just load like or train these models on much bigger data and with much more parameters. Parameters are roughly put are like embeddings, or I would say, I don't know how would I describe parameters, but parameters could be like dimensions on which you train a model on, right? So if GPT-2 is trained on 1.5 billion parameters, it's trained on like fewer dimension and fewer data set. A bigger dimension container can capture and absorb much bigger data set. So then OpenAI realized that what if I just keep on training it on much bigger data set? They started scraping the internet. They came up with GPT-3. And with that, an era of like scaling architecture came into picture, that uh, what if we just keep on training model on more and more data? Will they get intelligent? And as it turned out that they did, they got intelligent. So if you see, like if, for example, like to make things more relevant, if we come back to that same example, the cat sat on a mat, because a chat GPT-2 would say, or like a GPT-2 would say, because it was tired, it would just try to kind of wound up the answer within 3 words, mostly because it cannot carry like a long context window, because it's a smaller model with fewer parameters. And it's like computationally, it's very difficult for it to carry like larger context for it to answer. But if you take a bigger model with much more bigger parameter size, then considering GPT-3 or something, a similar answer with the GPT-3 could sound something like, because it wanted to rest after chasing a mouse all day. So you see, like now it can carry much bigger context window because it had more parameters. So the hypothesis that if you make a bigger model, it will work better, actually proved to be true. This is what has been happening till 2023 and 24-ish. I would say that bigger model, you put more money in, put more compute, more data, it will generate better answers. Soon after that, we realized that, okay, by we, I mean like researchers across the world realize that, okay, that if we keep on doing this, compute will become a bottleneck. Data collection will become a bottleneck, because data collection is not just simply scraping the internet, but it many times it also includes you kind of labeling that data. Now the internet is huge. You can't like make people sit and like label data day in day out, unnecessary, and also inefficient. Then they realize that what if we, instead of training one big dense model like GPT-3, what if we come up, or GPT-4 actually, what if we come up with a network of smaller expert models? That way, a model could be an expert in just, let's say, identifying animals or identifying a person or identifying a company, something like that. In that case, I will have a much less dense, much more sparse of a model. If I have a, let's say, if you assume this as a dense network of those smaller expert models, and you pass in this particular sentence, the cat sat on a mat, there would be a router like in the initial version of it, which will route it to one of the particular expert models. That way, only the expert models, like if in this case there is an animal, there is a verb, an activity, and there is a furniture mat. So only the models which are expert in, let's say, animal, an activity, and a furniture will get activated, and not the whole network will get activated. So you see, like where in GPT-4 or GPT-3, you were activating the whole dense model. Now you need not to do that. Now you need to just activate a smaller expert model, which can help you, if nothing, at least contextualize the representation. It will help you highlight that there is a cat, which is an animal, sat is an action which it did, and a mat is a furniture on which it sat on, something like that. So it will help you contextualize this. This is a lot of job done, right? If you just put in this contextualized representation into a smaller transformer or into a smaller model, it can answer you properly. So then researchers started experimenting with these kind of sparse models, which are fondly called mixture of experts. So you would come across this word very frequently if you're reading up most of the current days model like Quen or Deepseek R1. Uh, like not 100% sure, but they're supposedly built on these architecture, which is like mixture of expert. This makes it much easier for a user to inference it, or like use these models in production app, because it only activates a part of it much cheaper, much faster, and also like much better because every model is trained for those specific use cases. The output of these expert models could be used for, once you have this contextualized translation, a contextualized representation, it could be further put into a transformer, which could generate a new things using it, or it could be simply used for classification or identity identification. Like there are many use cases of it, depending on it. You can also be more specific. You can create a mixture of experts for a pharmaceutical use case or a healthcare use case or something like that. This architecture is highly effective, and as like only a part of it gets activated, you can store it in multiple places. You can store like a couple of expert in one data center, a couple of other expert in another data center. You can also kind of, it's sort of like caching them. You can cache them properly, which makes them highly efficient when it comes to inference, and much more cheaper because you're not like using the whole model, or user is not paying for the whole model every time they're using a model. They're paying for a part of it. Understanding this will give us a good leverage into understanding what DeepSeek is. So if we are good so far, or if you guys have any questions, please let me know. Otherwise, I'll move on. Cool. So now let's talk about like DeepSeek, and let's talk actually mostly about these newer models which came right after this, or which came leveraging the sparse architecture. If you remember, the last thing we spoke about was scaling architecture, where like companies were putting more and more data in, and then they found that it was not very computationally efficient. So we need to come up with better things. So researchers started experimenting with these mixture of experts. As a result, we came up with these more reasoning and specialized architecture models. Let's talk about GPT model first. Initially, like let's say this is GPT-O1, for example. So GPT-O1 would be built something like this, right? That there would be a trained model, pre-trained model, which would be something like GPT-4 or 4.0 or something like that. They haven't been very open about it, so the best thing I can do is like make best estimate based on whatever I've been reading on Reddit or some other blogs. But let's say they used one of the existing GPT model, let's say 4. They fine-tuned it for specific task, right? Because a pre-trained model would have a general language understanding, that it will understand how English works, how a person speaking English would structure their sentences or something like that. But it will not know what a particular, like what a specific task it needs to do. For example, if you ask it to reason, it does not know what a reasoning is. All it does is basically just understand English or speak English. So you can fine tune it. You can add like a smaller model on top of it, which is fine tuned for reasoning. So now you can kind of fine tuning could be very simply put something like where you are asking it via prompt to do something. So you are making sure that it at least asks itself 4 or 5 questions, right? So that makes it reason that it's not just one question and answer, but it's like I have prompted this fine-tuned model to not just give me the answer right away, but ask it itself like 4 more sub questions and then answer me. So this is like a very rudimentary form of reasoning. So then researchers at OpenAI and few other companies started putting these fine-tuned models which are fine-tuned for reasoning, right? Similar thing happened in Deepseek. We'll get into the difference just in a second. But similarly, like if you look at an overview of things, the overview looks pretty similar. That Deepseek used Deepseek V3, which is the pre-trained base version of a model. Then to build their then to build their R1, R10, at least the first one, they used a fine-tuning technique, which I'm going to talk about, to basically fine-tune it for reasoning, right? So overview is the same. Where the difference came, there were like actually multiple difference. So we'll go through them one by one. But the first difference, which I would like to highlight, since we were talking about architecture, was for OpenAI, they had like the GPT pre-trained model, and top of it, the fine-tuned model was again a similar dense model, which was fine-tuned using prompts, right? So it was a similar model, like pre-trained model, might be a smaller one, might be trained on a different data, but again, the architecture was the same, right? In DeepSeek, they did this thing very intelligently because they did not have enough data. So they probably used one of the available model which they had. So V3, it could be not as good as like 4, but then they used a different kind of architecture for fine tune, which was a mixture of experts. So they decided that I'll not train one big fine tuning model for it, for the whole thing. I would rather train experts for everything and then take that as a layer on top of my pre-trained model. So this was one big difference, which came in the which was evident in architecturally in both the models. This difference made DeepSeek much more faster and better in inferencing because now you have expert models. It's sparse, it's cheaper. If a user wants to use it, like for all the benefits which I spoke about earlier, they would only pay a fraction of a price when they're inferencing it. So this technique worked out really well for them. That okay, reasoning is better because now I have specific experts which will answer me, and it's very cheaper because I'm not activating the whole denser model, but like a smaller part of it, right? So this was the first big difference, which I hope will help you understand the architectural choices which DeepSeek made and which made them like kind of successful. But this was not the only one. If you guys have any question, please feel free to stop me. Otherwise, I'll carry on. Cool. So the next difference, uh, yeah, Tausif, you had a question?
Yeah, yeah,
Yeah,
yeah. So both of the OpenAI and DeepSeek are using a pre-trained model, right?
yeah.
Yeah. This mixture of experts is used during inference itself, right? And
So
here
yeah,
they are using entire dense model.
there they're using.
During inference time, I mean, for example, when we are prompting, during that time, mixture of experts is used to analyze the prompt and generate output from the pre-trained model.
Yeah,
That is what you mean, right?
yeah, yeah, exactly.
Yeah. So the pre-trained model, they are using it as what OpenAI has, or they have pre-trained their own.
No, they have pre-trained their own. So again, these things, I have read the paper, so I'm taking this example from the paper. DeepSeek is using DeepSeek V3, which was their base model, pre-trained model. They released this first, and then soon after that, they fine-tuned it to turn out to be like DeepSeek R1. GPT hasn't disclosed that which model they had used as a pre-trained model, but assumingly it's an OpenAI, so they might be using one of their previous model as a pre-trained model, or they might have like it's also possible that they pre-train a new model from scratch, although it's very expensive. But it's possible that a company can pre-train a model from scratch every time they have to build a new model.
Okay, okay.
Does that answer your question, or was I not clear?
Yeah, so what I was trying to understand, like where this price gap is coming, the huge price gap is coming, at which point exactly?
Yeah, so I'll take you through that. So the first difference is because that they are using for inferencing, they're using MOE, master of experts, mixture of experts, sorry, right? So inferencing is cheaper. Are you clear on that piece?
Yeah. Yes.
Right. Let me take you to the next slide. That like if you're talking about pre-training, let's talk about that as well. So that was
Okay.
the one architectural difference. The second difference came in fine tuning. So in complete disclaimer, the meeting will end in 10 minutes. So I'll probably have to, I will probably share like another link with you guys. And I'll try to wrap it up in 10 minutes otherwise. But yeah, so the fine tuning, like architectural difference, we understood right now, just now, right? Now talking about the fine tuning bit. So the second price difference which came was because they like the way you fine tune it is also different. Like architecture is okay that they use mixture of experts, whatever GPT use, like OpenAI use these dense model, but also how you tune it, how you train this smaller fine tuned layer is also very different. So OpenAI relied heavily on SFT. SFT is supervised fine tuning, and little bit of RLHF. RLHF is reinforcement learning human feedback. So that is basically if a person is using ChatGPT and say that the answer is wrong or the response is wrong, then they will take in that feedback and then they will like kind of absorb, like retrain once they have enough such similar feedback, then they'll like fine tune their model. So you see, so they did this, but most of the model, most of O1 was fine tuned using a supervised fine tuning. This is very expensive because supervised fine tuning ke andar, the like within supervised fine tuning, the supervised bit is where like a human will sit and label the data. That is a very expensive operation. I'll cover this SFT in a minute too. But in DeepSeek, they used SFT as minimum as possible. They called it cold start, which was like a labeled data, but this sample was extremely small, and they relied heavily on reinforcement learning. Now, reinforcement learning is, I'll come back to this slide in a minute, but let's say, let me give you an example of what reinforcement learning is. Let's say if you are a model and I don't give you the answer, like in SFT, you will know the answer. Like if I give you an instruction and I'll tell you that the answer is ABC, right? That is SFT. But if I give you a question and I ask you to kind of come up with an answer, and every time you come up with an answer, I can just tell you that it's right or wrong, or I maybe a degree that how right it is and how wrong it is. So I'm not telling you an answer. I'm teaching you a process to come up with that answer. And every time I'm giving you just a reward or a harm based on what your answer is. So that is like kind of course correction. This approach is cheaper. It's computationally expensive, but it does not take like that much of data. And if it works out good. So in DeepSeek's case, this computation, like they accepted this computational cost, and they were like, we'll still go with RL because we don't have access to that much of data. And this approach is what made their training or like fine tuning of their DeepSeek R1 much, much cheaper. So inferencing cost came down because of this. Training cost came down because of this. When they are saying that $6 million what it took them, that is because of this. That it only took 6 million because it did not have to take like label data from anywhere, or did not have to buy much of data. All they had to do is just put in more compute where they already had their clusters of GPUs available, and they just put that to work, and they use reinforcement learning to fine tune the model. Uh, did that clarify things for you, Tausif?
Yeah. Yeah.
Yes.
One question on that part. How will the rewards be awarded technically? How will the rewards be awarded? Because someone needs to say whether this is right or not, right?
Just 1 second, because this call is going to shut down. Surya, if you are in the call,
Yes.
Surya, can you please create a Zoom meeting and share in this group so that if call ends, we can join that group and continue our discussion.
Just give me a second.
Cool. Yeah. So, sorry, what was the question? Can you please come again?
Yeah. My question was, like, say, ChatGPT uses something like reinforcement learning from human feedback, right?
Yeah.
And is DeepSeek also doing the same thing?
Very,
And
very
if they are
interesting.
doing it, yeah.
So, the thing is, like DeepSeek R1 is effective on few things, right? You might have, if you have read the paper, you might have read that it's beating benchmark on STEM. STEM is basically science, technology, engineering, something, mathematics and stuff. So it's specific. It's doing really, really well in those fields where you have very established reward functions. So for example,
Got
if
it.
you ask, if you want to train DeepSeek on coding, then your reward function would be compiling. Like every time it comes up with an answer, you can easily compile and check. You don't have to get the code labeled. You have like whether it's working or not through compilers, right? So
Got it.
they came up with these kind of reward functions. That's why it does similar. Same thing goes for mathematics. Same thing goes for like most of the scientific fields. That you have these definitive answers which you can use as reward functions. So you don't need, like if I show you a picture like an art form, I would need a human to kind of label it for me, right? But if I just give
Got
you
it.
a mathematics question, bare minimum, all you will check, or like how our professors used to grade us in our college or school, is that they look at the final answer and that's it, done with it. They would
Yeah.
not go through most of the steps. So that kind of reward functions is what they chose. Again, it's mostly like based on my research. As things will open up, we'll learn more about what kind of reward functions they chose. But that's, I have a very strong reason to believe that they chose those kind of reward functions. That's why they are excelling in STEM fields.
Yeah. Thanks.
Cool. Moving on. So, just talking a little bit more about SFT and RL, SFT supervised fine tuning and reinforcement learning. So, supervised fine tuning also has like a lot of its benefits. Like it's stable, it's simple. Like you have labeled data, you can instruct a model to do certain things, right? It's safe. You know what you're getting into. Uh, of course, it needs a lot of label data, so only bigger companies can afford to do it. It can't solve problems which has not been seen before. Like if no one has labeled that problem, it can't solve it. Reinforcement learning, whereas can solve those things. It's much more creative. If you tell it scenario A, B, and C, it can kind of do D, E, and F on itself. But again, it's little difficult because it's like you have to be very smart in choosing your reward functions, as I just described. Training can go unstable. Like it is possible that you're training on and on, but nothing comes out of it because like you don't have anything concrete to start with, or like anything concrete to kind of evaluate against, right? So hacking is also a problem, that if you chose a wrong reward function, then your model will get trained in a completely different direction. Cost could become like compute cost could become much more expensive because it's not that you are optimizing for a particular goal, but you're optimizing for the process. So like that process could get much longer without you realizing that it's not the most optimal, right? So these are some of the basic differences. You can search them on Google. Guys, we have this Zoom call. Let's join this new Zoom call in a minute. And if we drops off from here, so please copy it and keep it handy. As soon as we drop from here, we'll join this call. Right. So now there was another difference between OpenAI and DeepSeek, which is distillation. Distillation is very interesting. Distillation has a role to play in how you fine tune model as well. But you would have heard of these models in forms of, like, you would have seen like Llama coming with like 7 billion, 8 billion parameters, then 150 billion parameters, 14 billion parameters. So all of these different versions, they're basically distilled models. What distillation simply is that you have a bigger, dense model and you want to come up with a smaller, much more specific model which can do certain things but much better, because it will be cheaper for you. It will be easier for you to host. You can probably host it in your laptop and it will be extremely cheaper, right? So that's why distillation is kind of top of the town nowadays. What OpenAI does is kind of like still like a black box. Nobody knows, but it seems like they're mini and turbo versions of their models are retrained. They're not like distilled, as in like they're not. Actually, let me cover DeepSeek first, then I'll come to this. That will make more sense. So DeepSeek model asks where like you built one DeepSeek R1, which was the parent model, then you have to kind of distill it into a smaller model. So what you did was you selected another smaller model, let's say Llama. Then you kind of use this bigger model to label data. That label data would go in here. Now, since it's a very specific model, let's say for a specific field, let's say finance, it will only have label data for that, which was again labeled by a bigger intelligent model. No human involved, no cost there. Plus would be much faster. Now, and DeepSeek also what it does is like it gives you a reasoning chain of thought, like how it is thinking about this, and then give you an answer. So that whole of that context plus the answer will get fed into this model. So without going through all of that reinforcement learning, it will still use a supervised fine tuning based on these answers and absorb most of the knowledge. So the digital model for a specific field would be as good as a bigger model. That's what DeepSeek does. OpenAI seem to not be doing that. Again, not sure since they are like not so open about it, but they seem to be retraining smaller models from scratch.